Court. Okay, so we're ready for you.
Thank you so much for the introduction, Wenmin. And then thank you so much for this opportunity to share one of our sort of the team's customer enablement stories on DGL Life Science to this like a big DGL community. So today, I'm going to talk about this algorithm called the potential net, which is on DGL Life Science package. And then it's more, I'm gonna talk more like the customization of the sample code to meet the rigorous like industry requirements. Like industry, what I mean by industry here is the R&D division of pharmaceutical company team. And then today I'm going to talk a lot about the modification in the original code from DGL library. And I probably need to apologize in advance to our audience that I may not be able to talk much about the results and numbers, but sort of the I just wanted to see sort of like, you know, that how I modified the original code, how the team modified the original code to make it more practice. So that's the main thing for today. Okay, so this is my bio. I'm a senior research scientist at Amazon Machine Learning Solutions Lab. Amazon Machine Learning Solutions Lab is like a customer enabling team. So we usually work with like external customers to sort of like start our, you know, start the ML, we call it like an ML machine learning journey together. So if your company has sort of like a problem into, you know, in terms of like initiating the machine learning projects in many ways, someone like me and our team just basically work with the subject matter expert from your team and and making the solution together. That's the thing. I have a PhD in bioengineering. AI actually was not my sort of the field back then. I've been involved like various different sort of the radiology and the medical physics related project before I joined Amazon. But then like right now, it's like I'm one of the specialists for like AI enablement in such a field. And then not only the medical imaging, I've been working with a lot of other projects such as like a gaming and sports. So that's the thing. All right, so today's talk is based on the module number 4 of the KDD hands-on tutorial from this year. So you can learn, so that, as I say, that you can learn like modifications, what made it, you know, what we made to make the original script from DGL Life Science library and become like a more practical. Okay, so here's today's agenda. First, I'm briefly talking about DGL Life Science. And then second, I'm going to talk about potential net, what it does and how it works. And then third, I'm going to share some tips to bring the algorithm to the real life application. And also like we are going to discuss like some of the blockers in terms of like industry requirements and the corresponding solutions. All right, so let's get started. Yeah, here's a DGL Life Science. This is a DGL community. Probably like many of you guys have already know a lot of things. But the DGL Life Science is a useful package for applying the graph neural network to various tasks in chemistry and biology, which is built on top of PyTorch, DGL, and RDKit. And as far as I see, there are three main use cases. Number one, molecular property prediction, which is usually like a toxicity, as well as like a solubility sort of a prediction of whatever the molecule. And second thing is the chemical reaction prediction. And then there are some like essence of molecular generation. And many of these use cases are often simplified into just like a message passing and then graph readout in the context of general graph neural network. So here's the thing. Here's the illustration of a message passing, and then graph readout and how the things used in DGL life science. So imagine here, yeah. So these nodes represented by gray dots are atoms, and then atoms are, oh, can I see cursor? Yeah, atoms are connected through the bonds, and which are basically edges, and then that makes up one molecule. So that's like a basically graph representation of the molecule. And then through the graph neural network computation. So those like a latent representation of these nodes are updated through message passing process. And then once like a message passing is done through many layers, and then node information is aggregated and forming a molecular level one latent representation, which is this one. And this like a last latent vector is going into the fully connected layer to compute either regression or classification model and so on. Then basically this is like one of the basic representation of like a many of the algorithm in DGL life science. So that was a sort of like a nutshell the basics of DGL life science. So then we are talking about the potential net. Like what is potential net? So potential net is a GNN algorithm to compute the binding affinity between ligands and proteins. So whether a ligand, which is the potential drug, binds to a target protein, which is a receptor, is a very important information for drug discovery or drug screening. And then there is a physics model, like a simulation software. So however, these software licenses tend to be very expensive and the throughput is not high. So the customer is seeking another option to much more sort of scalable solution. And so there is a the terminology called a hit or hit to lead, but hit. The customer wants to narrow down like a candidate drug, and out of like a millions or like around the hundreds of the potential candidate, and they can eventually use this like a physics model simulator, but at the same time, they would like to have more sort of like the filtering. So what they request from like a GNN solution is basically like a big throughput. And then in addition to that, the GNN model can be used the next process, so-called the lead. So the lead is to look through like a candidate compound through sort of like a similar structure. So you have like a one hit compound, and then you know its structure. So you want to test out the very similar structure around the hit compound to expand the basically candidate the compounds. Why you need to do that? Because you want to test the chemical property of those molecules, such that whether the compound is hydrophobic, hydrophilic, which is like a water soluble or not, or whether the compound is toxic or not. So you wanna test that, and the customer expect that GNN is particularly helpful because you can train in such a the property prediction model using the model that you trained for binding affinity prediction through the process so-called fine-tuning. So in that kind of idea that our customers and also a lot of people in the industry seeing that the GNN based the drug discovery has potential. So that's the thing. The GitHub page of the DGL Life Science provides an example of the binding affinity prediction, and it uses the potential net. So if you're interested, then like you should definitely check it out. Potential net uses the public data set so-called the PDB bind. So what is a PDB bind? The PDB bind data set is a collection of experimentally measured binding affinity data for biomolecular complex and deposited in the protein data bank. It provides like an essential linkage between energetic structure information of those protein ligand complex. And then here you see the example of the protein ligand complex, which is basically the input to the graph neural network. And then you can easily expect that those like a molecular structure is given as a graph. And then output is something like in this column, it's a number, which is the minus log KD KI. The KD is a dissociation and the KI is an inhibitory constant. So the basic binding affinity is expressed as a ratio between those two constants. And then this number itself is actually the output to the graph neural network. So basically what you're gonna solve, using potential net is that you have this the protein ligand complex as an input, and then you're trying to predict something, this number here. So the latest version of PDB bind dataset is like version 2020. And then there are like different tiers of a tier system, namely the core, refined, and general. And then qualitatively speaking, the core data set is cleaner than sort of a general or refined. But as you see, you only have a 285 the complexes, which is not enough to train. You can use like you can add 5,000 of the refined data set, and also you can also use the general data set, which has like the order of the 20,000. But sort of this like a public data set that kept on increasing, but we still needs it's good to have more. And then these are the public data set. And our customers in the pharmaceutical industry, they have their own data of the protein, so the ligand protein complex, as well as the binding affinity constant that they have. So they would like to sort of mix between their public data set and then their proprietary data set to sort of like to make it the better data set. Okay. So here's an illustration of how potential net works. There are two different stages in the message passing. The first message passing among the atoms belonging to the ligand. So this molecule is basically ligand, and then it computes the message passing here, and then once it's done, it goes to the stage 2, and then this is the at the stage 2. It is a message passing among the atoms in different distance bins, which takes in account the both covalent and non-covalent bonds. Since it takes into account the distance, it can take into account the interaction between atoms in like ligands and then the atoms in the proteins. And then once this like a stage 2 is done, you have a fully updated the representation of the atoms in a ligand, and then you have a graph gathering process and then fully connected layer, and then you calculate the binding affinity as a regression. So this is how the potential net works. Okay, so now let's go to the third part. What is the actual like a pain point in a real life application? So basically, this page again. DGL Life Science that provides a sample script, but what did our customer need to modify to meet their industry requirement? That's something I'm talking about. So the real life application in the industry and its brokers. So converting from like a basically toy example to the custom solution. There are basically 3 pain points. So one is the customizing a data processing pipeline, 2, customizing the graph neural network architecture, and the third is scaling up the solution. And then we can take a look at one by one. And the first, like a customizing a data processing pipeline. And so this is basically converting the PDB files, SDF and the PDB to the binary file. So original script from DGL Life Science, the Life Sci, loads the data directly from the PDB files, in which the extensions are either SDF or PDB. And by doing so, this is the PyTorch or like a DGL dataset looks like. So you have a list with the length of 5. And then the first index 0 is taken by the data index. So in this example, you see 2673, which is basically the number 73 complex. And then index number 1 and 2 are taken by RDKit mode data type. And actual graph component is stored in index 3. And then this is an important one. And then index 4 is the binding affinity number, which is basically the output to the graph neural network. So you actually need those two, the index number 3 and the index number 4. So our customer solution is basically converting these PDB files to the binary files. And also we refactor the data processing pipeline to create the binary files as well as the load the graph through the binary file. That's the thing. And then we also have the custom data loader for training. Another important thing is like a data anonymization. You can easily imagine that the people in the pharmaceutical industry don't want to share the precise information about their proprietary molecule. So those are the things that you don't want to share that. So despite like they being unnecessary for graph neural network training or like inference, the original script expect the PyTorch data set to have the index 1 and 2. The both are used for something like RDKit more the data. And then the RDKit mode data that basically shows something like this here. It's sort of the you see like a nice sort of like a chemical structure here, but they contain the information of a compound. And then in the pharmaceutical industry, this is basically like $1 million trade secret that you want to hide. So you don't want this. And then converting the PDB files to binary file to help our customer to hide these information on compound from the competitor. So we just basically get rid of those two. Other thing we did was that the shuffling atoms. So you see those like a nodes and the edges, right? And if you see the node as well as the node feature, which given as a one-hot encoding, you can actually see the which atoms are the correspond which atoms correspond to which the node. And so that's also the information the customer want to hide. And then the solution we provided was that we actually shuffle the order of the atom encoding. So atoms are encoded by one-hot encoding, like given like this. So you have like HNOCP. But by shuffling order, you can actually anonymize it. And by doing so, the trained graph neural network only works with the atoms in the right order. So once you change the order, and as far as you know the order, that you can sort of use a training inference, like a trained model for inference. But you don't know if you don't know the order, your model is basically nothing. Other thing we helped was that the customizing the graph neural network architecture itself. So earlier I said the non-covalent bonds are expressed in the distance between atoms. And then they were expressed as a different distance bins, which make up the adjacency matrix between edge. Basically it's a node. And which is basically the edges. The original DGL life-size script has a 4 different distance bins given the left-hand side here. 1.5, 2.5, 3.5, and 4.5 angstrom. So we took a suggestion from subject matter experts from the customer and then made it to sort of more finer bins between 2.5 and 3.5. So you see we have a 2.7, 2.9, 3.1, and 3.3. And it came up a lot of iteration to come up this, but it seems like this one works a little bit better. The other thing is that it's a scalable solution. So we modify the code so that our solution is compatible to Amazon SageMaker training instance. So it enabled vertical and the horizontal scaling. And Amazon SageMaker training instance supports like various types of the GPU instance. And you can also run hyperparameter tuning to come up with like a best sort of a set of the hyperparameters. And SageMaker also makes it easier for you to manage experiment. So again, today's talk is based on this module number 4 of KDD hands-on tutorial from this year. And it has many ideas of how we modified the example from DGL lifeside and made it something more practical so that the subject matter expert wants to use for their sort of day-to-day research activity. And then hope you are able to learn modification we made to make the original script sort of from DGL Life Science become more practical. Okay, so this is the last slide from me. In summary, DGL Life Science provides like useful tools to work on like many biochem the use cases like using graph neural network. And here's a potential net. The spatial graph convolutions exhibit like a sort of performance in like affinity prediction. And then the customized solution meets the industry requirements such as data anonymization, as well as a scalable experiment. And basically that's it from me. Thank you so much.
Well, thank you, Tatsuya. Very much appreciate it. Any questions, folks?